Welcome to AP Review for Solutions. We have two problems, actually two fairly lengthy problems. Today one is force diagrams, a little bit of circular now, and the other one is elevator forces. So these are, I'm trying to hit problems that are common, are important, and have pretty much a similar approach. Force diagram, express F net, solve for acceleration, use it in kinematics, or solve for another force. Okay, so this one is basically a Ferrous wheel where we have a book, they're zooming in on side, and it's going around and around in a clockwise fashion. And a little twist on that is they give us what looks like a simple harmonic motion. And it is, but it's not. It's really just a different way of looking at circular motion. So it's important that you make the connection here. Okay, so let me get as much of this in the frame as possible. Let's make sure we understand the setup. So if I'm looking at this particular book, right, and we're just looking at where is it horizontally compared to x equals 0, we can see at time 0, it's at position 0. And then if it moves this way as it moves up, right, in other words, it's moving in a general negative x direction, as we can see here, and then when it gets to here, it starts moving back towards 0, still in the x direction, and then when it gets to the 12 o'clock position, now it's moving horizontally forward to its maximum extent, which would be at the 3 o'clock position, and then it gets back to 0 there. And that's how we understand that. Okay, so what looks like a simple harmonic graph, a negative sign graph, is equivalent to moving in a circle where we just look at one of the components, in this case the horizontal component. If you get that, then that makes the problem a whole lot easier. Okay, so the first question I asked, I believe, I don't remember what the first question they asked was. Let's take a look at it. Is determine the speed, or the period. Okay, so the period, well, the graph, that's pretty straightforward, right? We can see that one complete period is right there, and that's about 120 or 120 seconds. Next question asks, what's the maximum horizontal speed? I'm pretty sure that's what they ask. Okay, so they don't have speed on that graph. Calculate the tangential speed, not the angular, okay? So we're not worried about theta in terms of radians per second. We want to know the tangential speed. All right, well, that's circular motion. In other words, it's always moving the same speed at any given instant. So this is really a kinematics problem. Okay, so if I want to get the speed, let's say right there or right there, and they asked us about period, well, then the speed for one revolution is simply how far it goes, which is 2 pi r, all divided by the period. Okay, so don't forget that's one way you can calculate the speed for something moving in a circle. We could relate it to centripetal acceleration, but that isn't coming to play here at all. Now the question is, what's the radius? This r, well, you can get that from the graph, and that is going to be the, if you will, the crest or the trough, the greatest amplitude. So that's 30. So that's simply 2 pi 30 divided by the 120, and then you can work that out and get an answer. Okay, so it might not be obvious at first, but don't make it more complicated than you need to. All right, next, now it gets a little bit more interesting. So we want to draw a force diagram on the book when it is at the lowest point, I believe. Okay, and they make clear that there's nothing pushing it forward. Okay, each force at the lowest point, the book is moving in a horizontal direction. In what direction at all is the net vertical force? Okay, and you have these. All right, so what you want to do is, we're going to label forces. That's a big dot, so I'm going to draw a dot here. We have the normal force up. We have mg down. And let's S up any other forces. Let's go through the list. Is there an applied force acting on it? And the answer is no. Okay. Is there friction? Well, there is. we're going to say no on that one because there's nothing trying to push it in the forward direction, so there's really no reason to friction for oppose it. If you might be thinking of centripetal force, well, centripetal force is not a force, it's just a generic name for the sum of the forces. So these are the ones that are trying to push it towards the center. In fact, the normal force is. Okay, so now in part 2, what is the direction of the net vertical force? Okay, well, you might be tempted to say that these two cancel each other out. They are definitely opposites, but they can't cancel each other out because if I represent the Ferrous wheel here and we're at this point, it's going in a circle, so it's got to be accelerating towards the center. And if it's accelerating towards the center, then the net force has to be upward or towards the center. So that means that the normal force is greater than the gravity, or the net force is upward. Okay. Next, derive an algebraic expression for the vertical force that the bench exerts on the book. In other words, the normal force in terms of the givens. Okay, so we've got our force diagram. Next, what was our net force? Well, F net, just looking at the diagram, is nothing more than the sum of those two. And since they're not the direction, we're going to subtract them. And I'm going to put N minus mg. Why that? Because I know that the normal force has to be bigger than the weight in order to accelerate inward. And what am I going to set that equal to? Well, ma. Since this is moving in a circle, it's a centripetal acceleration, so I can translate that to mv squared all over r. So what am I solving for? I'm solving for n. So n is going to be mg. I'm going to add it to the other side, plus mv squared over r. So there's our derivation. And then, I don't know if there's a part. Yep, at the lowest point is the force that the bench exerts on the book greater than less than the weight. Well, we already established that. We established that for reasons we talked about before, but this equation right here supports that. The normal force is the weight plus an additional amount based on how quickly we're accelerating. All right, so that's number 1. Pretty much circular motion. I like this because it reminds us a few things. A, we're always accelerating inward. Therefore, our inward force has to be bigger than any outward force if there is one. Applying the second law in terms of expressing F net and setting it to MA. It's really important we are able to do that for any situation. Okay, so this next problem is an old type of AP problem. I include in there because it had elevator stuff on it, and I thought it's worthwhile, and also some graphs. So we have an elevator moving up or down, and they give us position. I almost want to say that's velocity. Read it carefully, that's position, so I'm just going to put an x, okay, to remind myself as a function of time. And then they want us to sketch velocity as a function of time. So you got to do carefully. There's a lot of little parts here. So let's look at this before I scroll down. We have 5 distinct events going on. We have from 0 to 8, we see we have a straight line. From 8 to 10, we see that it curves, concave down. Then flat, then it curves again from 18 to 20, and then it's straight line again. So you want to have those 5 different events reflected in your velocity time graph. Okay, so I can't go back and forth very easily, but here is the first one. That's position versus time, so I need to find the slope of this in order to get the velocity, and I see it's positive. So if I look back at the numbers, I believe that slope is 1.5. So we're moving at a steady 1.5 meters per second, I believe, for the first 8 seconds. Then from 8 to 10, it's slowing down. I'm going to ignore that for now, but I know it goes to 0. And I believe it stays at 0 because it's flat up until the 18th second. Then it turns around and goes in a negative direction. So what we'd want to do is we would want to transition at the 20th second to the new velocity. I don't remember what that new velocity is or the slope. I'm just going to guess it's -2. Okay, you can work that out, and then it's going to be flat for whatever time is remaining. So there is 3 of the 5 points, then, or 4 of the 5 points. We have the right value, we have the right shape, we have 0 for this time interval, and we have the right value, right shape for that. Then we got to draw in a transition. So during the time, 8 to 10, it's accelerating, and then it's accelerating this way. So there's our velocity time graph. Okay, And then the rest of the problems are just basically calculate average acceleration. So acceleration rate to 10. You could find a slope of this graph, that would work. Or you could just say A is delta V over T. We know before it started accelerating it was moving 1.5. At the 20th second or 10th second was not moving, 0, and that took 2 seconds. So there is your acceleration. And since it's slowing down while it's moving forward, the acceleration has to be down. And then they ask, calculate the apparent weight of the passenger at time equals 4. What is apparent weight? It's not the actual weight, but it's the normal force. Right? I'll use Fn. That's what we have to remember. Fn is equal to what? Well, if we go back up to the 4th second, actually I can use this right there. Right, we see we have a constant velocity. That makes life a lot easier. If it's constant velocity, then the normal force has to balance the weight. So the apparent weight is the actual weight. So you might be thinking in an elevator, well, apparent weight is going to be different than a weight. It can be when we're accelerating, but if it's not accelerating, then we're fine. Okay, that sums up these two problems.